good morning, afternoon, and evening, depending on the time zone. This is Daniel, and this is the Zero Knowledge Learning Group. It's like a learning group on different zero knowledge topics and SNARKs, most practically in application development and programming. And today's topic is a little bit like, kind of a fancy topic, I would say. It's like how to create like decentralized AI with like zero knowledge machine learning. It's actually one way of creating like AI, or more specifically, zero knowledge integrated with like blockchain applications. But before going or plunging into the details, let me just talk a few words about this zero knowledge learning group. So practically, it's throughout this year. It's in every month, always the first Thursday, or most likely the first Thursday. We start from 6 o'clock Central European time. That's like 9 o'clock Pacific, and I don't know, it's probably like 1 o'clock New York and 5 o'clock London. The structure or the logistic is, well, so not too overcomplicated. We always have like 1 hour. It's usually just a presentation. We might as well have time for a short discussion, but sometimes it's just not manageable. But if you have like questions, we got a Discord channel. I'm gonna show you just in a second, at Linux Foundation Decentralized Trust. So basically, feel free to issue any questions on different zero knowledge topics in these Discord channels. I mean, supposing we don't have the time in this 1 hour for that. We are covering different topics on zero knowledge proofs, mostly from a programmer and application developer perspective, with some theory. So I'm not a mathematician myself, so I won't cover very deep theoretical things, most like from programmers, application development, or architecture point of view. So generally, the coordination, you're gonna find meetups on the Linux Foundation Decentralized Trust at meetup.com. That's like for a monthly basis. We just host these sessions in Zoom. And what's more important, we are having one Discord channel that's at the Linux Foundation Decentralized Trust. So I mean, this is the link, but basically, it's just easy to get there. If you just Google for Linux Foundation Decentralized Trust Discord channel, then you can get an invitation. And if you have like access for the LFDT channel, then practically we are somewhere under communities. That's gonna be somewhere here, the community tab, and then just the last community tab is like the zero knowledge learning group. So again, it's practically a chat, and then supposing that we do not have time for discussing things in detail, then just feel free to post here anything or ask here anything, or just have conversation in different zero knowledge topics. So that's one thing. Meetup.com is the second one. So that's like meetup.com. You will find these 1 hour sessions practically announced in each month. And last but not least, we are having repository. The repository is at Linux Foundation Decentralized Trust Labs. So labs are practically small projects from Linux Foundation Decentralized Trust, and you can find a ZK learning group. And ZK learning group is practically all the materials that we cover here, practically the presentations, the recordings, some literature. Sometimes we have like sample codes as well, so you can practically find everything here. So just feel free to take a look or even contribute if you want. So that's the logistics. I mean, the plan is that we keep it till the end of the year, and then practically we will have like 2 more sessions probably. That's the logistics on a monthly basis. So we started somehow in February with some introduction. We covered at the beginning some theoretical basis like polynomial commitments, interactive oracle proofs. And we started somehow with programming in May. We covered like 2 general SNARK or zero knowledge programming frameworks. One was Circum and the other one was NOIR. And from September, we started to investigate different applications. We started with proof of reserve, proof of solvency, proofs in September, and then we continue now with like zero knowledge machine learning. And the plan is that we're gonna have some roll-ups, especially ZK roll-ups in November. And in December, there's gonna be a wrap-up, perhaps for further applications. And then we take a look how it continues next year, if that continues. So that's the logistics. And then let's just start with the agenda for today. It's again, so if you expect like machine learning or artificial intelligence in a general sense, it's not gonna be here. We are focusing on zero knowledge applications. One special area which is like zero knowledge machine learning, and we investigate how zero knowledge machine learning can help us to build like a more decentralized zero machine learning or more decentralized application intelligence in a sense. But again, this is not a course on generally on artificial intelligence. Okay, so that's the agenda for today. We're gonna start with ZK SNARK. Then we have one slide on what is actually zero knowledge machine learning. Then we have applications. Then we just dive deeper in different zero knowledge machine learning models. It's like private input, public model, private model, public input, and some other scenarios like private model and private input or zero knowledge for machine learning. I mean for the learning itself, not just for the inference. And then we investigate how this can be integrated with like blockchain protocols, and we investigate how things can be integrated with layer 1 and with layer 2. I mean, especially layer 2 roll-up applications or roll-up protocols. And at the end, some challenge, links, resources, literatures as usual. And yeah, usually we have like questions and answers at the end. It's a little bit questionable if we have time for this, but supposing we do not have time for Q&A, again, I would encourage everybody just to join to the Linux Foundation Decentralized Trust Discord channel, and then just have any questions in these zero knowledge learning groups on different zero knowledge topics, or on these sessions, on these presentations. So let me start from the beginning, and usually I have one slide as a summary. I mean, we covered all of things already, but anyway, just as a brief introduction or just as a summary of a previous sessions, I usually have one slide, which is like ZK SNARK. ZK SNARK means succinct non-interactive argument of knowledge, and ZK means like zero knowledge. So in this model, again, it's just 5-minute summary on the course previously, or on the sessions previously. Usually we think of like two actors. We get like, I mean, usually in cryptography, we get Alice and Bob, but in this scenario, we have a prover and we have a verifier, and the prover tries to prove something in a way that this proof is small, is easy to verify, and it might have some hidden properties as well, especially like hidden inputs or hidden secrets. One example is like, for instance, I claim or a prover claims that she knows, I mean, Alice claims that she knows like the pre-image of a hash function, and she creates a cryptographic proof to convince the verifier, to convince Bob that she really knows this input, and Bob will be convinced that at least the prover really knows this pre-image of a hash function, but basically the pre-image will not be revealed, so the pre-image will not be known by Bob. That's like a pretty easy or a pretty simple example. And so there can be many different like zero knowledge applications and domains. So basically we have something we usually want to express somehow our domain knowledge, our business problem. It's like knowing a pre-image of a function or having some kind of a zero knowledge machine learning or something. So usually we express this business logic, this domain logic with a computation. And while as zero knowledge has a lot of like deep mathematical constructs, this computation is for the first round not a simple programming language, but it's usually something which is like arithmetic circuits. Usually we have an arithmetic circuit as a computation. This is a computation. It has one public input or a lot of public inputs, uh, a private input, which might be again like a vector of private inputs actually, and this computes to f. Sometimes it is expressed as computes to 0, which is more like a predicate formulation of the same problem. And this is like pretty, mathematical computation. So usually what we do in real life zero-knowledge programming, that we have like a framework for this programming. So basically we start with a high-level computation, again, which is not necessarily directly arithmetic circuit. We formulate our problem somehow, then we compile things to a lower level application, which is like zero-knowledge, which is like arithmetic circuits. And then we compile things to an even more abstract format, which is like polynomials, and we can have all the properties of our SNARK, of our zero-knowledge computation, expressed by polynomials in a mathematical sense. And usually, if we think of like this scenario, we get a prover, a verifier, and a proof. So prover and verifier, in a more mathematical sense, are actually algorithms. So we have a prover algorithm. The prover gonna takes like, so there's like there might be one pre-processing step. This is PP and VP, which initialize the whole structure. But anyway, generally the prover gets like public input, which can be one public input, but you can imagine that this is like a vector of public inputs, a private input, and it generates some proofs. And basically we get another algorithm, which is the verifier algorithm, that takes, again, there's some pre-processing steps as well, but it's not so important. But the verifier gets the public inputs, it gets the proof. It's important that the verifier doesn't see the private input, and the output is either accept or reject. So either the verifier Bob gonna be sure that Alice really knows the preimage of a hash, or not. So it can be that it is rejected. And this is a logic of SNARK, of ZK SNARK, and we got some properties, of course. So I mean, it should be like succinct. That's like probably the most important. Succinct basically means that the size of this proof is small, and basically this verification process is pretty fast. So basically, it has like many applications, but if you think of like blockchain, basically you usually have like kind of a complex computation that can be run outside blockchain, and then you can import the result into blockchain, and it can be verified on chain. Again, due to these succinct properties, which means because the proof size is small and the verification process is small, so practically you can store the proof on chain and verify it on chain, but basically we can imagine that the computation might not be feasible to run on chain. And we have some other properties. It's like complete. Complete means that if like Alice really knows something, then she can basically create the proof, and Bob will be convinced. And knowledge sound is like the other directions. So basically, if Bob is convinced or the verifier is convinced by a proof, then basically Alice really or the prover really knows like a fact with which this proof was generated. And we have one more, which is zero knowledge. Again, zero knowledge is like an optional property. So this private input is property and is optional. And there are use cases where like a private input makes sense, but there are use cases where like private input is not necessary at all. So this was like a brief summary, and then let me just take a look on zero knowledge machine learning. So we're not going to cover machine learning, just on a very high perspective. But basically the idea is that we got some data, we get a model, And what we do, so for the first round, we can train this model somehow. It can be like a supervised or a non-supervised training. And then basically we get a trained model. And if we have this trained model, then we can do some kind of an inference. So for instance, there's like this mimic model. It's the most classical, if I'm not mistaken, for recognizing number from 0 to 1. But you can imagine as well that basically we train our neural network, artificial neural network, like pictures, and we want to recognize cats. And basically, if we decide that, okay, our training was successful, in a sense, then we have a trained model, and we want to use this trained model as an inference. So basically, for a given picture, we want to identify if that's picture, if there's a cat on this picture or not. That's a very, very simple high-level introduction. But basically, from an architecture point of view, we could distinguish two parts. We have a learning phase, which can be, again, depending on your neural network model, can be supervised or non-supervised learning as well. And we got another phase as well, which is inference. Inference is simply an input is associated based on the trained model. So how can we put like machine learning, or how can we put like zero knowledge and ZK SNARK into this machine learning? So the general idea is that we want to do something offline, and basically we want to bring the result online. And we can have like many different areas or combinations. So we can basically train. So we can use the training phase, having off-chain, and we can make the inference, even the inference off-chain as well. And we can basically bring different like zero knowledge proofs, either on the fact that the model was trained somehow correctly or convincingly, or we can even bring like zero knowledge proofs on the fact that the inference was somehow executed in a correct way. So there are different combinations. Different spins might be supported by zero knowledge proofs. And the point is that, I mean, independently, if we create like a proof for training or for inference, basically the proofs and the results can be validated in blockchain application. It can be like on-chain. And again, there are like many combinations. So we can imagine, I mean, training is like a little bit more heavy, but even if you just have the simplest example, which is like inference, we can imagine that there can be many options, many different combinations, especially because we can think of like SNARK without zero knowledge properties, and we can think of like SNARK with zero knowledge properties. So even with this distinguishing, we can think of like public models with public inputs and public outputs, and we can think of like private models with public inputs, and we can think of like public models with private inputs, and we can think of like use cases where both our model and our use case are private, or input are private practically. Usually the out is public, because you want to bring this output somehow to the top of blockchain, and you want to verify that it was really inferred by like an algorithm. So the question is, why do we need it? Why do we need such applications? The reason is for that because basically, if you think of like a little bit like decentralization, then you can imagine there's like a lot of logic that can be executed on chain in a decentralized way. So if you think of like DeFi, like decentralized finance, practically your protocols are implemented on the top of blockchain. It's like if you think of like I don't know, like a liquidity pool based decentralized exchange. The point is that basically your whole algorithm is implemented on chain. So basically it has like kind of a trustless properties for your whole application, for your all logic. Basically, I mean, that's what the point of DeFi. You don't need to like trust in like any kind of counterparty or institutions, but basically you need to trust in the code, which of course has some advantages and of course disadvantages as well. but basically that's the point of your whole DeFi movement. And if you imagine, there's in DeFi there's usually like building blocks as well and the interoperability as well. So basically these protocols usually are implemented in a way that they might interoperable somehow with each other. So if you think of like that you want to bring like machine learning or AI algorithms into this ecosystem, into the DeFi ecosystem, then practically what you would need to do is to have like the same trustless guarantees as your DeFi application. So basically, if you have like one DeFi application, again, it's just having one example. We create somehow kind credit rating for kind of a user based on, I don't know, like transaction graph analytics or something, which is processed by AI. And this is like kind of an off-chain oracle, supposing that we want to bring this result on-chain. Then the problem is that even if like 90% of our DeFi application is on-chain, is decentralized and trustless, there's like one element, which is like, I mean, pretty heavy because it's like pretty impactful because it's like credit rating for our users. But this application runs practically off-chain, and it just doesn't have like the same trustless elements than running everything on the top of blockchain. So supposing that you want to bring like AI and machine learning into DeFi applications in a way that you have the same trustless guarantees, then basically what you can do is to run your models outside the blockchain and import these models into the blockchain, but basically harden these inference or learning with some zero knowledge proofs. So that's the idea. Again, and this is a kind of decentralization of AI. Of course, there are many other ways how you can decentralize the AI. So this is just one special blockchain and ZK specific way. There might be, and there are other ways, other more famous ways as well how you can decentralize the AI. But this covers just this special example. Some other examples are, so imagine you get something which is like an on-chain asset management service. You get a portfolio, and the portfolio is rebalanced somehow in an automated way. So usually you can, I mean, in such applications, what you can do, you can implement your application in a way that your portfolio is rebalanced by some humans or based on some expert or even community decision. That might be an option. It is possible that your portfolio is rebalanced somehow in an algorithmic way. But then, of course, the problem is that you can implement just pretty simple algorithms on chain. And as soon as you do something complicated, so for instance, you want to rebalance your machine learning, you want to rebalance your portfolio with like machine learning, then of course your computation goes off chain. So basically you need to have or you should have the same trustless guarantee as if it would run in on as if it would everything run on chain practically. So that's like the use case. Some other use cases as well. You can imagine something like AI-driven AML for DeFi protocols. It's again that's like AI-driven AML should run, of course, off chain, but there should be a way that we verify that the inference or that learning was correct. That's like that goes a little bit like in DeFi embedded supervision with self-regulatory protocols. It's like pretty much a research topic actually. But you can think of other use cases as well. So for instance, you have like biometric identification for on-chain protocols. Usually it contains some AI, some machine learning, and basically that should be proven or imported into blockchain in a trustless way, even in a private and trustless way. So basically there should be some zero knowledge hiding properties as well. But you can think of like IoT device data integration into the blockchain. See, if you have like IoT devices, you don't just import everything and put everything on chain because it's not manageable, but you have probably serious pre-processing steps, usually with machine learning, and that can be a use case as well. But you can think of like agents, AI agents as well. So supposing you want to somehow verify your models or AI agent model, then that can be a way as well, like using zero knowledge machine learning or something similar. So let's just go more into the details and let me investigate the different models. So the first model, again, so we start just with inference because inference is simple. So this is like inference. Again, we got a model, we train somehow with some data. Perhaps it was even like self-trained in a non-supervised settings. And basically we got a model. And what we want to use this model is to do some inference. Again, like there's an input, which is a picture, and we just want to decide if this picture contains a cat or not. So one model is the so-called private input public model. In this setup, it looks that way, that basically our input is private, so it should not be revealed, but basically our model is public and it can be verified by everybody. And basically the inference phase is supported by zero-knowledge proofs. We got some parameters of the trained model, so it's like a neural network. Then you can imagine that these are practically like the settings of or the learned settings of different neurons. And then basically the input is private. It's not even on chain, but basically we want to prove that this public model processed our input data, and basically the output data is a result of an unknown input data, which is processed by this neural network. And we want to process the output data and practically the proof that was executed somehow in a correct way on chain. It's kind of like if you think of like credit scoring, we might as well use something similar. So we say basically we learn somehow a neural network. We just train somehow, and basically we don't want to hide how basically the model itself. So we can say that hey, the model can be actually published, but what we want to do, of course, if we rate somebody, then we want to, I mean the somebody, and again, if that's like personal data or it's just like kind of a blockchain analytics data of a pseudonym actor, it doesn't matter. Usually we want to hide this somebody. We just want to make sure that basically this somebody is hidden, but we want to create a zero-knowledge proof that basically the same model used this somebody and created like credit scoring basically with a kind of a previously learned machine learning. And in this sense, what we can do, we can as a step zero, we can commit the parameters of our machine learning in like for instance the blockchain. So for instance, we can even publish our whole trained model, but this is usually like not necessarily the best step. So what we can do, we can publish like the hash of the parameters of our machine learning model, and we put the rest of the model like to a decentralized storage. It's pretty much the same. Even in a decentralized storage, our model, our trained model, gonna be public. As a next step, we can commit the private input hash. Again, it's just a hash, and basically, as a last step, we can give like a proof that basically the hash that was committed into the ledger is really the input with which the open or published machine learning was learned, and basically with this combination we really have like an output which is like X. So basically about this process, we can give like a zero knowledge proof, and then basically this zero knowledge proof can be verified on chain. And if that's verified, then somehow this output can be accepted practically. So again, this is like one model. We can think of another model, which is more, I mean, exactly the opposite. It's a private model, public input setup. In this sense, I mean, just think of like something which is like intellectual property. So let me imagine that in our situation, we just train somehow this model. Of course, it's a good question how people can verify if that was trained in a correct way or not. But anyway, let me just skip this problem for the first round. And let me just imagine that we want to keep this trained model practically secretly because we think that's like, that should be done like by intellectual property, or we just spend a lot of time for training. So basically, we don't want to publish this model to the public or to our competitors. We just want to keep somehow hidden. Okay. And then in this sense, what should be proven somehow that basically we use always the same model. And again, how it can be verified by the public, even if they don't see the model, that it's a right model or not, or if it's a good model or not, that's like a different question. But basically, in this setup, what we verify with zero knowledge proof is the fact if our model is the same. Okay. So basically, we created our model, somehow recognizing picture of cats. So basically, we don't publish our neural network parameters, but what we do, we just commit a hash of the parameters of our private machine learning model. This is like the hash of our parameters. And of course, we do not publish the parameters themselves. So we do not publish the parameters even on a like decentralized storage, of course. We just keep these parameters private. And as a next, we're just gonna give a zk SNARK proof that the X input produces a certain output by applying the machine learning model, which parameters were committed into the blockchain or publicly committed as a hash of parameters. So again, in this situation or in this model, the idea is to give a zero knowledge proof about the fact that we use the same machine learning model. And again, to decide, for instance, if that machine learning model is good or not, we can use some kind of another rating. For instance, just imagine the fact we want to recognize cats and we have a hidden model. So basically, we give like people like an option, like you can just test the system like, I don't know, 10 times for free, and then basically they can just test the system 10 times for free. And if they give like pictures 10 times and the system recognizes cat 10 times, then basically we can say, hey, that was the free period, so you can make a decision if you want to buy our service, our inference service, or if you don't want to buy our inference service. And after that, basically it's gonna cost money. And what the zero knowledge proof is about is to give a proof that you use or the customer uses the same neural network, the same trained neural network as in the first 10 free of charge inference. So that's all. That's practically the use case. Okay. So these are the easy use cases, but of course there are like other scenarios as well. They're just gonna be more and more complicated, of course. So we can think of like private input, private model. So of course, if both the input and the machine learning model is private, it's like a combination of the previous two pretty simple use cases. If you think of like healthcare applications, yeah, I mean, of course, a healthcare application, practically everything is private, of course. This use case is of course more complex, so you need something which is like a computational zero knowledge proof or multi-party computation. So it's this use case is like a little bit more tricky. You can have something as a public input, public model. In this sense, we use the fact that basically inference is a little bit more costly than like verifying the proofs. So basically, if that's a big model, it should be inferred once, and then basically the recognizing the proofs, just verifying the proofs on chain will be simple, more simple. So for instance, for computation intensive models, there's like a succinct proof of computation. And of course, like more interesting is like proof of training. It's pretty much in research. I mean, the whole field is of course in research, but proof of training is absolutely in research. But there are like initiatives as well, proving that like our model was trained in a very in a special way or in a way having like some parameters. Okay, but I mean, I would say uh, the field is in research, but if you just think of the two simple models, which is like private input, public model, or private model, public input, there are applications for these two models as well. So the next question, which comes from an architecture point of view, is how to integrate zero knowledge machine learnings into blockchain. And then basically, again, just for the first run, just think of these two simple use cases. We got a trained model. We might as well have something like private input and public model, and private model, public input. So let me just assume we have like these two or perhaps even three use cases for the first run. And let me just handle these use cases more or less as black box. So from an architecture point of view, again, focusing from blockchain, there might be two ways to integrate this. And one is like layer one integration. And of course, the second one is like layer two. So layer one integration, and again, just as a vision, our vision is not to combine like different neural networks and give like something as a very big neural network. But again, the vision and the architecture is here to have AI machine learning computation to be integrated into blockchain applications with the same trustless guarantees as with your DeFi logic, as with your decentralized finance logic, or as with your on-chain logic. Okay, so it's like a special niche area of like decentralized AI, I would say. But anyway, one way is like having layer one integration. So I mean, you might as well say, hey, I mean, we don't really need this whole stuff because I mean, we got like general purpose blockchain systems with smart contract capabilities. So we might as well implement our neural network actually on chain. Well, that's an option. And then, well, theoretically, you could do it. You could do that. Basically, the whole machine learning is realized as smart contracts. But usually, most blockchains have like scalability problems in terms of the code that can be executed on chain, in terms of the data that can be on chain, and so on and so forth. So it might not be the best option, but despite you can integrate machine learning in layer one architectures with like zero knowledge machine learning. And then to imagine zero knowledge machine learning in layer one integration, imagine the fact that you have like smart contracts in the systems, but instead of smart contracts, we have machine learning models. So practically, if you think of like Ethereums, you can deploy like kind of smart contracts, which there's like a smart contract call, and you can create practically your smart contract code. So instead of deploying smart contract code, just imagine that you deploy machine learning models on the blockchain. And basically, your model is not even stored on chain, but basically it's stored like either in a decentralized storage or it is stored practically. Uh, it is not, it is not necessarily stored practically. It might be stored just by special nodes or something due to privacy reasons. But again, so the idea is somehow that instead of deploying smart contracts to the blockchain, there might be like a special command deploying machine learning models. And basically, if you execute machine learning models, I mean, let's just use the analogy, like executing smart contracts on the blockchain. Instead of executing smart contracts on the blockchain, we just execute machine learning on inputs, producing output proved by ZK. So in a very simple model, and again, there might be like a lot of small details that are not necessary, I mean, well defined, but in a very high level, what we can say, let me just imagine like a Nakamoto consensus. In a Nakamoto consensus, we just pick node practically in each round. So this node not gonna like execute smart code for us, but basically this node will execute machine learning inference, for instance. And basically, based on this machine learning inference, it creates like a zero knowledge proof that this inference was executed in a correct way. So in a sense, our block might not look like that, hey, we got like some inputs and then we just executed basically like a smart contracts and we have like a new state. But basically our block might contain something similar as input, machine learning or inference, and basically some output. And some of these parameters might be even hidden. And instead we got something which is like zero knowledge proofs. And even if these parameters are visible, they are not necessarily written into the block, rather just hash values written into the block. But basically, we give like zero knowledge proofs that this inference was in a sense executed in a correct way. And that's what our leader does in a Nakamoto consensus. And basically, based on this block structure, everybody can verify that our execution was correct in a sense. And again, what is exactly this sense? It depends on your zero knowledge machine learning model. So that's like one idea of creating like zero knowledge or integrating zero knowledge proofs with like layer one integration. Uh, of course, there might be some considerations because I mean, one question is, yeah, of course, what about with the block time? So it might take like, I mean, in a classical blockchain, you just want to have like as fast or as small block time as it is possible. But like executing a machine learning model and generating proofs on that might take like, I don't know, minutes or even 10 minutes or even like in a very big model like ours. So like block time is a little bit questionable, but there might be like structures where we use like not just one block time, but somehow different block times as well. Or actually, I mean, if we say like layer one integration, we can think of something which is not just necessarily layer one, but it's like a multi-chain system. So in a multi-chain systems, you have just one big layer one, but you have a lot of layer two blockchains. So again, these might be not rollups, but layer two blockchains. It's like in Polkadot, the parachains. So in this sense, you can create something which is like a domain-specific sub-blockchain of an ecosystem. So we can think of this structure not in a general purpose blockchain system integrated with machine learning models, but in a way that basically there's like a domain-specific sub-blockchain which is integrated by a lot of other domain-specific sub-blockchains as well. And this sub-blockchain is created just for one purpose, just to execute these machine learning inference algorithms. And in this sense, it might be not such a big problem if our block time is something which is like minutes or even like 10 minutes, because eventually this sub-blockchain is domain specific, focusing just on these inference models. So basically, if you want to have like coins in transferred in seconds, you just use another sub-blockchain, not for this special purpose. So that's like idea for layer one integration. And we can think of something which is like a layer two integration. In a layer two, it's I think more like rollups. So basically not just sub blockchains, but basically I think of rollups. So in a rollup system, what we can do, we can have like different characteristics. So basically a rollup looks that way, that usually we have a blockchain, and then basically we have a rollup which has like a sequencer. Sequencer is doing like things off chain, usually transferring coins or tokens. And then basically sequencer gives like a proof somehow into the blockchain that basically the execution, again, this is like the off-chain execution carried out by the sequencer. So the sequencer gives like a proof, a cryptographic proof that what was executed is correct in a cryptographic sense. So, and usually in a token or in a or with a coin example, what you do, you got your blockchain, you just export somehow like tokens or coin or crypto to our sequencer, and there's like a cryptographic proof here that basically you exported this coin in a correct way, in a cryptographic sense. Then there are some state transition or token ownership change that is carried out by the sequencer. And about these changes, there's always like kind of a cryptographic proof. It can be usually like a Merkle tree proof. And basically, eventually, you get an import where you bring back your tokens or your balance into the blockchain. So that's in a very general sense, that's how like layer 2 rollup works. And then if you think of like machine learning, you can have like the same ideas or similar ideas, as previously. So first, we say that we don't deploy we don't export like tokens to this rollup, but we export like machine learning models, and we export like data to the blockchain. So it's pretty much in analogy as deploying machine learning models to the sequencer, to the rollup system, or exporting data to this rollup system. Uh, and then basically we execute inference on the rollup system, and this is pretty much the same. So we got like inputs, we got like machine learning models, and we got like outputs, and then in the next round we got like inputs again that might be even like the output of our previous inference, and we got like machine learning models and some outputs and some inputs and some machine learning models and some outputs. And of course, about each steps, we should create kind of a cryptographic proof, in a sense that that was like executed in a correct way, but with like combining Merkle proofs and zero knowledge proofs of the inference, this is doable. So it can be done basically. So eventually, we can prove that each step, each inference in this roll up was executed in a correct way, and there's always like a proof on that, again, like combining Merkle trees or hash trees and zero knowledge proofs of zero knowledge machine learning. And eventually we can import these elements back to the blockchain. I mean, especially probably some output data, which is important in our blockchain applications. And that's it. So that's basically the second idea for integrating blockchains with zero knowledge machine learning. Of course, if you think of like the very simple models, there might be even questions like how we can set up exactly like the private input public model or public model private input. So how much is it really public or private if we think of like sequencers? But I would say so these are details to be worked out probably in details in one application. And of course, if we can have something other than like just inference, like machine learning, I mean, that would be surely like a top application. So that was like the hard code or the hard content for today on machine learning, zero knowledge machine learning, and blockchain integration, and bringing things a little bit decentralized. Again, this is not exactly the same direction as most of the decentralized AI applications or ideas cover. It's like more like bringing or running our machine learning or AI model in a trustless way in order to bring that data into like DeFi applications with the same guarantees that can be guaranteed on-chain by the on-chain logic. Okay, so that was all. I have one demo application on ZK machine learning. Actually, we can just take a look very shortly. Sorry, that should be here. This is a very simple on-chain application. So this is a very simple demo. So what I'm doing, it's like MNIST. So practically, I'm just drawing like numbers. It's just a pretty tricky with Firefox, but that's gonna be like, that should be like 8. And basically, let me just take a look if I can create 8. And if I just say classify and prove, that takes a while. And basically, there's a prediction again. So this was like the input. The model is hard coded with like the verification and with the zero knowledge proof. So the prediction is 8, and then basically this is like a zero knowledge proof of our computation. So yeah, it's a pretty simple demo. It's not integrated with blockchain, of course, in any sense. So this was the demo. There's of course a challenge, as this is a zero knowledge learning group. So basically, if you investigate and experiment a machine learning model hardened by zero knowledge proof, and two examples are Noir and Circum, because we covered Noir and Circum in our sessions. So practically, if you think of like the awesome Noir repository, you will find here machine learning algorithms, and then there's like GitHub repos as well for Circum machine learning as well. So that's all for today. We have some links, resources, and literatures. And basically, thank you very much for the attention. If there's like any questions, then we have like, I don't know, five minutes, so I can try to answer. I mean, you can just use the chat as well. I'm just learning. I'm just reading the chat. Uh, the question is if you can use it for non-supervised learning. So I'm not quite sure if there's like models for non-supervised learning, but if you just imagine the idea, theoretically it's possible, because basically just imagine we have like so mostly focus on the inference part, and from the inference part, it doesn't matter if the model was trained in a supervised or a non-supervised model. So like classical example is like, I think classification is like the most classical example for non-supervised learning. Classification identifies if your input is in one category or in another one, and it doesn't matter if, and that's practically the inference part. It doesn't matter if it is, if it is done. I mean, if the learning was done in a supervised matter, like with, I don't know, learning with or teaching neural network with backpropagation algorithm, or if that was like set up by non-supervised learning, and the clusterization is based on non-supervised supervised learning. From an inference perspective, it doesn't matter. Uh, of course, it might be questionable how this non. I mean, if you focus on the learning phase, but again, it's very much like heavyweight research. From a learning perspective, there might be differences if that's a supervised or non-supervised model. But from an inference perspective, I would say there's just simply no difference. So I don't know. I'm just reading actually the chats. So basically, yeah, there were some issues probably with my voice. Sometimes it's just tricky. Yeah, sure. So basically we're gonna post everything. I will update the GitHub repository as well here. Again, but basically I can post it here. You will find here everything. Sometimes we email for the participants as well. But basically I just remember this repo. Everything is collected here, included like the slideshow, the presentation, the recording, example applications, links and literatures, and so on and so on and so forth. So basically, if you just remember this repo, you will find here everything. Or if you just remember the Linux Foundation Discord channel, I will post everything into the Linux Foundation Discord channel as well. So you will find everything. Yeah. So again, so this is the resources. You will find all the recordings and all the practically everything. You will find here everything. Okay. So I would say then that was for today. Thank you very much for your attention. And then again, if you have like any questions, just feel free to use the Discord channel. I will try to answer all of the questions as fast as I can. I wouldn't promise like exact timing, but yeah, as fast as I can. And then again, thanks a lot. We're gonna continue then next month, probably with like zero knowledge roll-ups. So thank you.
Thanks, Daniel. Thanks, everyone.